so we're going to just go through here and taking a look at it, this Desmos window. I put this Desmos file and a link to this available on our course page. I have a folder that's just named Desmos Graphs. And so this is one of the links that are available for this. So let's take a look at just pairing up some of these trig functions with their reciprocals and seeing their shape. So we're going to start with the sine function. And we can kind of see when we walk through these kind of the properties that we already kind of know about. So let's take a look. This is the sine function. Let me make sure we're in presenter mode. This is our sine function. The sine function goes forever in both directions. This is a cyclical function, meaning that it's going to go through the same pattern every 2 pi units. So think about this going around the circle, where as we go around the unit circle, our sine function is going to be equal to 0 in 2 different places, and then get back to that same 2 pi, which is really 0 for us. Our sine function is also going to be equal to 1 at pi over 2, and it'll be equal to -1 at 3 pi over 2. So those are the same things that we would have seen in the unit circle, but these are just the graph on our coordinate plane now. The function that we would associate with our sine function is the cosecant function. That's the reciprocal function. So CSC is the reciprocal function. And the reciprocal function, we would graph kind of above and below the peaks and valleys of our sine function. So the secant function looks like this in orange. And the secant function will be undefined where the sine function is equal to 0. So notice where our function crosses 0 at 0, at pi, and then at 2 pi. Each of those positions has an asymptote or a vertical asymptote for the cosecant function, because the cosecant function would be undefined if the sine function was 0, because we take the reciprocal to find the cosecant. So there's our pair of sine and cosecant functions right there. So you'll want to at least be able to identify what a cosecant function looks like on a coordinate plane. All right. Is there any questions with the graph for these two functions?
So on any of our tests,
What's that?
do we get to use Desmos on any of our tests?
You can use them on the unit tests. For the if you wanted to use them on the unit test, I'm okay with that. For those proctored exams, you'll just be able to use a hand calculator.
Gotcha.
All right. So let's take a look at the next ones. So we'll start with the base of the cosine function next, and we'll walk through that cosine function. The cosine value, we'll notice that the cosine function starts at a value of 1. So we start at a cosine value of 1. We will reach that cosine value back at 1 by 2 pi. And then both at pi halves and 3 pi halves, the cosine function is 0. So that's where we hit the peak of our unit circle and the bottom of our unit circle at 3 pi over 2. So that would be our x value would be equal to 0. And then at pi, our x value is -1 in our unit circle. And again, this repeats over and over again. So this graph, that same pattern goes over the next 2 pi to 4 pi and 4 pi to 6 pi. It's going to have that same shape. If we look at the secant function, the secant function will be graphed over that cosine function. So it'll look kind of similar to the last one. And for this one, we'll have our asymptotes at every pi starting at pi halves. So pi halves, 3 pi halves, 5 pi halves will have an asymptote for that secant function. So the secant will be our reciprocal for cosine, and so those are kind of graphed on top of each other. Okay. Is there any questions with the cosine and the secant graph here?
It looks like the secant graph is not connected to each other. Is there
So the secant graph does connect to the cosine graph at 0 and pi and 2 pi and 3 pi.
the secant graphs, it's represented by the yellow curve, right?
So the secant graph is the orange graph.
Yes, orange.
Yeah, and then the cosine is the blue.
Secant graphs, they themselves are not connected to each other, but it connects with the cosine.
I'm not quite understanding.
They look separate.
What looks separate from what?
The secant graphs, which is represented by the yellow curve, they are separate each other.
Yeah, so they are different graphs. So these sections of the graphs will be separated from each other.
How come the cos are connected to each other, whereas the secant is separated each other?
Right, yeah. So the secant will not be a continuous function. It will have sections to it. That's okay.
Okay, yeah. Thank you.
All right. Let's see. We'll go through one more, and we'll try to make a distinction. Two are kind of similar. The tangent function and the cotangent function, they work a little bit different. So I want to make a distinction between these two as we finish up here. The tangent function, we'll notice, has those same asymptotes. The tangent function, notice it's kind of a generally increasing function. So the tangent is an increasing function where we are set equal to 0 at the origin 0. And so it has kind of that S shape in between negative pi halves and pi halves. And then it repeats itself over and over again. So it has what we're going to call a period of pi units, because it's going to finish each cycle of tangent in pi units instead of 2 pi units. And have asymptotes there at every pi. The cotangent function is going to look a little bit different. It's just going to be kind of flipped around, but it will also be kind of shifted a little bit as well. So let's change over to the cotangent function and see the difference here. The cotangent function starts at pi, 0 to pi, and is kind of a generally decreasing function. So you can see that there's a bit of a difference between those two. If we kind of threw the tangent function back up, notice that the tangent function in purple is a generally decreasing, or a tangent function is generally increasing from left to right, and that cotangent function generally decreases from left to right, starting at 0 to pi. So we'll want to be able to distinguish between those two functions just on their regular graph. So we're not going to do a ton of work with tangent and cotangent other than just identifying which one is which. So we'll want to be able to do that. And again, you can reference this Desmos graph after class as you're working on assignments. These Desmos graphs are available in the folder on our course page. All right. Is there any questions from these basic graphs that I could answer for you guys?
Yes, really quick. In the notes, it says under sine and cosine functions, there are no vertical asymptotes.
Right, yeah. So for the just graph the sine, that's a good question. Just graph sine, notice that it is a continuous function. The asymptotes are for the secant function or the cosecant.
Oh, got it.
Function.
That makes sense.
So those would have the asymptotes because they have the breaks. But if you just graph the sine function by itself, it's a continuous function. There's no breaks in the graph.
Thank you.
Yeah, so I just wanted to associate those together because they kind of work with each other in terms of their graph. But the sine and cosine function, you're correct, don't have any asymptotes. Okay. Sounds good. All right, so let's take a look at our notes to get started. And we will start in just taking a look at some properties here. Start with some terminology for our basic trig functions. So in terms of our domain and range, vertical asymptotes, just in the notes, our domain for both of our functions, that means all the possible inputs for sine and cosine, we'll notice as all real numbers. So those sine and cosine functions are defined over the whole x-axis. So we can work with all numbers for these. The range for the sine and cosine function, we noticed, just was bounded from -1 to 1. And so that makes sense because we've been working with a unit circle, which is a radius 1 circle. So it's at most 1, and the smallest it could ever be is -1. So that's our range. And then no vertical asymptotes. The tangent function, on the other hand, we did have vertical asymptotes, and they happen to be pi halves, and then every pi after that will have to have an asymptote. So this is what this expression is. We'll have an asymptote at pi halves to start, and then we'll have another one at pi halves plus pi. So that would be 3 pi halves. Another one at 5 pi halves, and so on. And again, to the other direction as well. So you can go in the negative direction or the positive direction. You're going to continue to have those asymptotes every pi units starting at pi halves. The kind of next important concept that we'll talk about for these graphs is the period of the graph. And we'll specifically turn our attention to sines and cosines at this time. We're not doing a ton of work with the tangent function other than just identifying it. But we'll do a lot of work with the sine and cosine function and manipulating the graph or transforming the graph of sine and cosine. The first thing that we could transform is the period. So let's look at the definition here. The period of a sine or cosine function is the smallest segment in the x-axis that it takes for the function to complete one full cycle. And so generally, one full cycle of a sine and cosine function is done over a 2 pi interval. So 0 to 2 pi is usually the period, or 2 pi units is the period for any sine or cosine function. So over intervals from 0 to 2 pi, that would be talking about our period. So generally we'd say p is equal to 2 pi for these. But as we change kind of the formation or the equation of our sine and cosine, that period value can change. And we'll take a look at that today. The second thing that we can change for our function is the midline of our function. So the midline is really defined as midway between the function's maximum and its minimum. So for this function that's graphed, our midline here would simply be y is equal to 0. So that x-axis here happens to be the midline for this regular sine function. It's midway between my maximum and my minimum. And this should be just y equals 0 instead of x equals 0. Another thing we can change is the amplitude. So the amplitude of a sine and cosine function is the vertical distance from the midline to the maximum height of the function. So it's the midline maximum. And so right now, the amplitude for the sine of x function is just 1. You'll notice that we just increase 1 unit from top to midline. So even though the graph goes over 2 units of height, the amplitude is just concerned with kind of half of that height, or the midline to our maximum point. So those are the 3 items that we're going to focus on today. I don't think we're going to do any other properties today to get started. This is just another chart of looking at the general starting points for the domain, the range, the amplitude, and the period. So you'll notice that the sine and cosine function have a period of 2 pi to start with. The cosine and sine, the tangent and cotangent have the pi units as a period. So it does a full cycle of those 2 functions in a pi units. And then our reciprocal functions are also 2 pi for their period. All right, is there any questions with just the introduction of these properties? Any questions with the period, the midline, and the amplitude, and what those are referring to?
Yeah, sorry, real quick. How come you changed the x equals 0 to y equals 0 again?
Yeah, so the y, it's the midline is always the horizontal line of the function. So it's this line horizontally that goes through the middle of our function. So it's got to be a y is equal to x equals 0 would be the y-axis here, and we don't. That's incorrect. So that was a typo for me.
Oh, okay, okay. All right. Thank you. Thank you.
Yep. Anything else with these properties before we go into some examples? Okay, so this says we want to use the graph of sine to find all the values, and we're going to be using other functions, so it's not necessarily using sine the whole time. We want to find all values of x between 0 and 4 pi. So we want all values between 0 and 4 pi for the following, for which the following equations are true. All right, so when I consider each of these, I want to just really sketch these out maybe on our kind of a unit circle plane. Most of the time, that's going to be kind of the easiest way to get these done is kind of sketch them like we've done before, but we're now extending our domain to 0 to 4 pi. Meaning for each of these equations, we're actually going to get 4 solutions for our angle value. Since going around the unit circle, we would get 2 solutions for every value. This is really thinking about going around the unit circle twice, and so we'll want to use some ideas of coterminal angles to get kind of 2 extra solutions from the second rotation of our unit circle. So let's just dive into the first one and kind of just build a sketch of what the sine of x equals -1/2 would look like. The first thing I think about doing, we can think about looking these up on the unit circle since they are the common side ratios for us. We can also just remember what our principal acute angles are for the 30, 60, 90 triangle. So if I was to look at sine of x is equal to +1/2, what is the angle that gets that done? What is the sine? What angle gives me 1/2 with the sine function? If we've memorized those acute angles from 30, 60, 90, and 45. Yep, that would be the sine of 30, exactly. Yep, so sine of 30 degrees, so x is equal to 30 degrees, or in this case, we want solutions from 0 to 2 pi, so we're actually in radians. Whenever it asks us for solutions from 0 to 4 pi, we do want to present this into radians. So what would be the radian version for 30 degrees? And Anya, I think you're close, but not quite. Yeah, there it is. Yeah, pi over 6. So this is equivalent to pi over 6. All right. So pi over 6 really is, I'll kind of do this in dot, is our reference for this side length. And now we want to consider, well, I don't really want where the sine is 1/2. I want it to be -1/2. So what are the 2 quadrants where my sine is going to be, oh yeah, that's right. This should be 60. Sorry about that. I don't know why. Should be 60. We should flip that. Cosine of 60. No, we're right. We should be 30. Should be 30. There we go. So we do have for the positive part, but what 2 quadrants are going to give us a -1/2 or negative for? That's what we're searching for. What 2 quadrants would we be looking in there?
2 and 4.
So our sine function is definitely in 4.
It'd be 3 and 4. 2 is actually a positive because it's all students teach calculus or whatever.
Right. Yep, so
It's
all students take calculus. So yeah, so it would be the 3rd and 4th quadrant. That would be correct. Yep. So we want to really put this reference angle into those quadrants. So we'll put that reference angle here. That's pi over 6. right there, and then we'll put that same reference angle in the fourth quadrant. Excellent. And now we just want to determine what two angles that we just drew in blue are. So let's start with that first one in the third quadrant. If I wrap this around, that green angle that just formed in the third quadrant, this is going to be pi units all the way down to the x-axis. So that would be right 210, or how would we represent that in radians? Because we do want our final solution in radians. Pi plus pi over 6. We can think of this as 6 over 6 pi. So if I add 6 over 6 and another 6, that's, yep, Adrian, you got it. So 7 pi over 6. So let me just call this angle x1. So my first solution is going to be 7 pi over 6. 7 pi over 6 in green. Excellent job. If I take a look at the next angle, the next angle goes from 0 all the way around to my second angle there. So remember, this would be called 2 pi all the way around our circle, but I'm not going to go all the way around. I'm going to go all the way around except that last pi over 6. So what would be the radian angle that's drawn in red there? And we'll call this x2. Yep, that would be right. Yep, 330 would be the degree, or yeah, 330, and 11 pi over 6 would be this. 11 pi over 6. So that's just 2 pi minus pi over 6. Excellent job. So those are our two first solutions for this question. But we'd like to go out and find a couple more solutions, because remember, we like to get solutions from 0 to 4 over 4 pi. And so the next thing that we want to do is finding coterminal angles for both of these two solutions. If I can find a coterminal angle for both of them, then I can find the next set of two solutions. So remember, when we think about coterminal angles, usually we're going to be adding 2 pi to the existing solutions. So if I considered adding 2 pi to both of these solutions, again, 2 pi is really 12 pi over 6 for us, because we're having a denominator of 6. So that's a way we can think about adding our fractions there. So let's take a look. We'll have x3. If I do 7 pi over 6 plus 12 pi over 6, what will be my third solution here if I do a coterminal angle for x1? Yep, that would be 19 pi over 6 for the first one. Excellent, so that's one solution. And then let's do one more solution. So x4, if I add now to x2, and I want to add that same 12 pi over 6, I think we'll get 23 pi over 6 just by adding those two fractions, 12 pi over 6 and 11 pi over 6. And there would be my full set of 4 solutions from 0 to 4 pi. And we can just do a double check here that notice that 4 pi is equivalent to 24 pi over 6. So each of those angles are between 0 and 24 pi. So we're definitely safe with those 4 solutions. So those would be what we'd want to enter. All right, looks great. Is there any questions I can answer with part A here? Yeah, the 12 pi over 6, this is equivalent to 2 pi. So I'm just turning that 2 pi into a number that's helpful to add to my current numbers. So 12 over 6 is still 2.
So just to get this clear, when we're looking for all solutions between 0 and 4 pi, that's basically looking for all solutions within 2 circles of it. So all 4 solutions twice around the unit circle, correct?
Exactly. Yep. So we're fine. The first 2 are in the first round of our unit circle, and the second would be just a second trip around at those same 2 points. All right, excellent. So let's look at maybe one more at least. I think we have a couple more here. So cosine x equals square root 2 over 2. We want to do the same exercise. So let's start with a picture, and then we'll try to identify where we are equal to square root of 2 over 2 in our first round of our unit circle. So where do I find cosine equals square root 2 over 2 first on our graph? Where do I find that ratio? Since this is not negative, we don't have as much work to do here. Where is our cosine going to be equal to root 2 over 2? Yep, 45 degrees, and we will be getting solutions in the first and fourth quadrant. You're right, Anya. So if we think about all students take calculus, we're going to get solutions in our first and fourth quadrant. Excellent job. And they're going to be at 45 degrees, or 45 degrees is equal to pi over 4. So we want to get used to kind of working with both of those. So 45, think pi over 4. So let's put that together. We'll sketch the first one. We'll just use blue. So 45 degrees, or pi over 4. And then we know we can draw that same reference in the fourth quadrant, because that's also where our cosine function is going to be root 2 over 2. Excellent. All right, so let's see. Let's find what these solutions are going to be. I think the first one, x1, well, x1 is just where it is. Notice that that's just going to be pi over 4, no changes to that. How about our x2? What is the second angle that's formed in the fourth quadrant?
Seven pi over 4.
Yep, 7 pi over 4. Excellent job. Would be 7 pi over 4. All right, and now we're looking for some coterminal angles to these existing angles. So again, if I think about adding 2 pi to each of these? Well, the first one we could say x3. Third solution we could get if we add 2 pi would be 2 pi plus pi over 4. I believe that would be 9 pi over 4 for the first solution. And then what would be our last solution, x4? If we had a coterminal angle for 7 pi over 4. Close, Adrian. Really close. Remember that 2 pi here is really
11 pi over 4.
Yeah, so I think we'll have 15. Yeah, 15 pi over 4. Because 8 pi over 4 is the equivalent of the 2 pi, and if we add 7 over 4, that gives us 15 pi over 4 for that solution. So we'll have pi over 4, 7 pi over 4, 9 pi over 4, and 15 pi over 4 for those solutions. Going around the unit circle. So
Mr. Kroger, I got a question. Where'd you get 8 pi over 4 though? How did you get 15 pi for quadrant 4? You went from 9 to 15. How?
So these two are connected. And these two are connected. So the first solution, pi over 4, if I add 2 pi, that's equivalent to 8 pi over 4. So 8 pi over 4 and 1 pi over 4 give me the first coterminal angle. And then I'm going to be adding 8 pi over 4 again to 7 pi over 4. So that's where I get the 15 pi over 4. So 8 over 2, or 8 over 4 is equal to 2. That's all I'm doing there.
Sounds good.
Yeah. So I'm always going to just convert the 2 pi to whatever fraction is helpful for us to add. It's a lot easier to see the addition for the coterminal angle if we just convert it to an improper fraction and then add. Kind of hopefully a helpful technique. All right. Let's see. Yeah, let's do this. So I haven't done this yet in our class, but I think this is the opportunity to jump into something like this. So we have one more problem, and for this, we're going to do just a little bit of group work. So you guys are going to get a chance to interact with each other just a little bit. So go ahead and just jot this on your page, and we'll go through this after you guys have a chance to take a look. But I'd like to have your guys to think about putting some input into this. So I'm going to put you guys into some breakout groups through WebEx here. And you guys are going to be able to kind of sketch this out and talk to each other about the solutions for tangent equal to the square root of 3. So let me put you guys into breakout groups, and then we'll just do this for maybe 7-8 minutes or so. You guys will get a prompt in just a little bit to join some groups. And create those. So you guys should find or you're going to receive a little notification. You guys can jump into those breakout groups, and then we'll come back in just a little bit to discuss. Any questions in here so far?
Yeah, Mr. Krogan, I got a 240 as a degree, and it was 4 pi over 3. So I guess we're going to go next time.
So you got 4 pi over 3 for one of the angles.
Yeah, if you do tan of x on the rad 3, it's angle 240, and it would be 4 pi over 3.
Okay.
And then the other angle would be pi over 3 on that.
Right. Yep. So your first one should be in the first quadrant, just pi over 3. I think that's good. Then you just want to go out and find those coterminal angles to those angles.
Yeah, but that's my question again. How would you? That's what I was confused. How would you find those? How would you find those coterminal angles?
So then for that, you would add 2 pi to each one of those, which would be like adding the fraction 6 pi over 3.
Correct.
So then the cotangent of the first one would be 7 pi over 3.
Yep. Yep. You're exactly right, Adrian. Right on the money. Yep. So just adding 2 pi to both of those angles will work.
So is the coterminal side 5 pi over 3?
Not quite.
The fourth one? Are you going to the fourth quadrant, or are you going to the first?
So you're going to have really 2 solutions that are going to be in the first quadrant, 2 solutions that are in the third quadrant. So if you started with your pi over 3 and added 2 pi, I think you're getting 7 pi over 3. So those 2 solutions are going to be found in your first quadrant.
I had a 2 pi mystery and I got 6 pi over 3 though on the first one. So I didn't.
So 6 pi over 3 is 2 pi. So you didn't add the pi thirds. So pi over 3 plus 6 pi over 3 should give you 7.
Wait, now I'm really confused. Where did you get the pi over 3 then?
Because that's your first solution.
Okay.
Yeah, so you're always adding to your given solution in the first round of the unit circle. All right, well, I need to check on a couple other groups. We will regroup with this problem just a little bit. Any questions in this group so far? Feel like we're on track?
Yeah, I think we're still working on it. Yeah, I think we're good.
Okay. We'll circle back in just a little bit. I'll check on a couple other groups. How are you guys doing in here? Any questions for this problem?
I'm doing all right, thank you. I believe I have all the
Okay.
answers already.
How about everybody else? You feeling confident with what we got?
I'm starting to understand this a lot more than I did in the beginning.
Good, good. Good to hear. All right, we'll circle back in just a little bit.
Good.
How are you guys doing in here? Any questions I can answer?
Yeah, I think we are in the right track.
Okay, cool.
Yeah.
Feel good? All right. We'll just bring everybody back together and we'll see what you guys have. All right. Welcome back, everyone. So what were we finding for maybe the first solution to this equation?
Pi over 3.
Pi over 3, okay. So 60 degrees or pi over 3 would be our first solution. Great. So this would be really we'll call it x1 is pi over 3, okay. And where would we find the second solution for this, for tangent? Anyone else have a second solution?
I found the second solution in the third quadrant. I got 4 pi over 3.
Yeah. So if we pick that same reference angle and through it here, all the way around here, this would be pi plus an extra pi over 3. So this angle x2 would be 4 pi over 3. Excellent. So there's our second solution.
Looks like somebody's audio is not working that well.
Oh no. Hopefully it comes back. Hopefully it's clear for most everybody here. All right, so now we want to think about taking some coterminal angles to these. So if I wanted to find a fourth solution, what would be our coterminal angle for x1?
Seven pi over 3.
Yep, 7 pi over 3. So these coterminal angles, if we add 2 pi, or equivalently, we can think about adding 6 pi over 3. Those two numbers are the same. So that's 7 pi over 3. Excellent. For the first coterminal. And what about the last one?
Ten pi over 3.
10 pi over 3. Excellent. 10 pi over 3. Sweet. So we have all four solutions sitting there. Feels good. Those are all. So you'll notice that we don't necessarily need to, have a unit circle here to be able to solve these. We really just need to have those kind of the basic ratios here available to us, and then use the concept of reference angles and coterminal angles. So that's kind of a nice thing to think about, is we really have the unit circle in a way memorized. We can figure it out just by using those other properties. So let's take a bit of a break here, and you guys are welcome to stay on and ask a few questions if you want, but we'll come back and start this next section up at 9:05. And so you guys can take a break, get some water, stretch your legs, and we'll be back in just a little bit.
Mr. Krogan, could you scroll up a little bit? My computer lagged, so I didn't get to the top.
And I'll get some water as well. I'll be right back with you guys.
Yet, are you still there?
Yeah, I'm here.
Okay, do you want me to explain a little further or no?
I think I'll be good. I'm probably gonna go to tutoring after this.
Okay, just wanted to help.
Alright, thanks though. I really appreciate it.
Thank you. I just barely got it myself for like the last second. I'm like, oh wait, now I know, figure out what and know what you're talking about.
You're good.
Thank you. Bye bye.
Professor, I got a question.
Yeah.
On the midterm, is 3.5 gonna be on there? Because 3.5, or is it 4.5? Yeah, 3.5 I think is after the midterm.
So in terms of when you're assigned it or when it's due?
Like the questions are the questions on 3.5, even though it's after the midterm, are they still gonna be into, like, you can see like 3.5, like chapter 3 still continues after. Oh no, sorry. Oh, I'm sorry, I got mixed up. Sorry, I meant the Unit 1 test. Unit 1 test.
Yeah, so Unit 1 is just Chapter 1 and 2.
Oh, just chapter 1 and 2? I thought it was also 3.
Yep.
Okay.
Yep. So Unit 1 is just Chapter 1 and 2. Unit 2 will be Chapter 2 and 4, or 3 and 4. So they're just
Okay.
2 chapters each.
Okay. Thank you for clearing that up.
Yep. All right. So let's get started again. We will go into section 4.2 with looking at these two properties of amplitude and period on our cosine and sine graphs. So let's begin. We'll talk through a few definitions and then get started. If you guys are with us, go ahead and give me a thumbs up and we will get started. So the first thing we'll talk through is just the format these functions will come in. The equations of sine and cosine we'll see with these coefficients of a and b. So either equal to a sine bx or a cosine bx, where a is signifying the amplitude and the b is affecting the period. So the period itself is 2 pi the absolute value of b. Most of the time, this b value is going to be a positive number. So most of the time, the absolute value doesn't necessarily matter a whole lot. But by definition, it is going to be an absolute value there for the b value. So again, amplitude is the height of our function from the midline to its maximum. And the period is really defined as how long a single cycle of sine or cosine is. So we can say the period is defined as the length of one cycle of, we'll call it sine or cosine, depending on what we're working with. And the b value, we can interpret as just the number of cycles that happen in 2 pi. So if the b value is 1, then we're just going to have 1 cycle in 2 pi. And the period would be 2 pi. So those two things we want to make sure are separate. The b value is not exactly the period. The period is 2 pi divided by that b value. So those would be how we define both of those. So the period is the length of 1 cycle, and b is the number of cycles that happens in 2 pi. If this b value is larger than 1, then the graph will be compressed. And if the b value is less than 1, that would mean we would stretch. So, for instance, if the b value in an equation was equal to 2, well, that would mean that we're going to be compressing because we're going to be having each cycle, or at least 2 cycles in 2 pi units. So that would mean our single cycles actually compress by 2 times the length. because we need to get 2 cycles in 2 pi units instead of just 1. So let's consider a couple graphs, and we'll just get our feet wet with graphing a few of these smaller graphs, and we'll compress or kind of increase the complexity as we go. So if I consider this first graph, and I just want to graph it over the domain of 0 to 2 pi, the first thing I want to highlight is what is the a and the b value for the equation. So with 4 sine of x, what would be the a and the b value in that equation?
Four and one. 4 for A,
Yeah.
1 for B.
Yeah, so here a is equal to 4 amplitude and b is equal to 1. So we have a regular period of 2 pi. Again, period is just equal to 2 pi divided by absolute value b. So this would happen to just be 2 pi for us. So we're just doing 1 full cycle in 2 pi. And we have an amplitude of 4. So the first thing I can do to my graph, if I'm just sketching it, obviously you'll be doing this on the computer, so you'll probably want to do a sketch of the graph and then relate that into the program. So we can turn this amplitude here into 4 and -4 if we're sketching this on paper. Just call those units 4 and -4. And I'm just going to want to draw a sine function with that amplitude. So a couple things might be helpful. As I considered the unit circle, and I considered some of these cardinal directions. So the first point here is 1, 0, 0. Up at the top, we would have 0, 1. Over here, we'll have -1, 0. And the last one is down below at 3 pi halves. That would be 0, -1. So it might be nice to keep this in mind to think about kind of how the sine function works here. Remember, the sine function is associated with the x value or the y values. So we start at 0, 0, or starting at 0, we go to 1, 0, back to 0, and then back to -1 for those y values. So when I look at each of these angles, notice that this is 0. This would be pi halves. This is pi units. And this is 3 pi over 2. This would tell me there's really kind of 4 sections of this graph. If we have a starting point at 0, we're going to start at 0. Then the sine function is going to increase to 1, or what we'd call the upper amplitude. So instead of 1 here, that will actually go to 4. If I said 4 times the sine of pi over 2, this would be 4 times as the sine of pi over 2 is equal to 1, just based on our unit circle. So this would just give us a height of 4. And we'd be up to at 4. We'd be back down at 0 by pi units. And then we'd be down at -1, or in this case, -4, because our amplitude has changed at 3 pi over 2. And then we'd come back to 0 when we hit 2 pi. So these are kind of the points that we would consider when we graph our sine function, if there's no shifting left to right here. And then the program will do the graphing for you once you hit it with a few points. And consider making our curves here. To finish out this graph. And that's what our sine function over the 0 to 2 pi interval would look like. Is there any questions with that graph, just expanding the amplitude there?
I had a question about the math real quick.
Yeah.
For 4 sine comma over 2, how come you change that to 1 again?
So the 4 sine pi over 2, that's right?
Yeah.
Yeah, so sine pi over 2 is equal to 1 based on our unit circle.
Oh, okay, okay.
And so we're just expanding the amplitude to 4 instead of just 1. So everything on our unit circle would just be multiplied by 4, and that's where we get our amplitude.
And you said we're able to find that out on the unit circle?
Yep. Yep, so those are just our points on our unit circle at each of those angles. So
Okay.
1 comma 0, 0 comma 1, negative 1, 0, and 0, negative 1.
Okay, all right, thank you.
So, Professor, when you have a number in front of sine, like 4 sine, is that just like a vertical like stretch, like a vertical shift of the graph higher, like stretching
Yeah, I
of
guess
it?
you could call that a vertical stretch for the amplitude. It's just going to stretch the graph 4 units in both directions, up and down. So it's really, we call that an amplitude change, but you can kind of think of it as a vertical stretch if you want to. All right, any other thoughts before we jump to another function? Take a look at a cosine function next with a 1/2 amplitude, and you'll see the difference here. So again, it might be, as we just get started, it might be helpful to draw that unit circle again, those points of 1 comma 0, 0 comma 1, and so on. So in this case, we are looking at a cosine function, so the shape is going to be a little bit different. And notice that we'll have an a equal to 1/2. And our b values, again, you're just going to be 1. So our period is still just 2 pi. So we're going to go through the whole 0 to 2 pi units with 1 cycle. Since we're thinking about the cosine function, now we're considering the x values. So the x values at each of these angles, 1, 0, negative 1, and 0, and then back to 1. So one thing we can start with is just consider changing our amplitude. So this would be, instead of 1, we'd have a 1/2 and a negative 1/2. So there's my amplitude change. And then we're just going to follow my x values around the unit circle. So the cosine function starts at the amplitude. So my cosine function actually starts at whatever my amplitude is. So that would be starting at 1/2. then we go to 0 at pi over 2. And then we'll be down at -1. In this case, it's -1/2 by pi units. And then 3 pi over 2 will give us another 0. And we're going to be back up at a 1/2 unit, or the amplitude, by 2 pi. So the shape is definitely different, or it's a shifted shape. And we start our amplitude and end back at our amplitude for the cosine function. So bringing this together as a graph, we'll have a graph looking like this. So when we think about cosine functions in general, we always start at the amplitude, or we start at the maximum or minimum. So if it's a positive amplitude, we always start at the maximum. If it's a negative amplitude, we start at the minimum. The sine function that we just did before, notice that that started at the midline. So if we have a sine function start, this will always start at the midline. All right, is there any questions I can answer with the cosine function here? All right, and I just mentioned here that it either starts at the maximum or minimum. So notice that this amplitude A is a 1/2. And so that would be a positive, therefore we started at our maximum. The next one, we will have a negative amplitude, and we'll see what change that makes to a graph. So we'll keep with a cosine function. But this case, we have an A value that's equal to -2. Our amplitude is really the absolute value of this A. So the amplitude we would still call +2. So amplitude in general is still +2, but we do want to take into account that the A started as a negative when we go to graph it. So this one, we want to, again, change our values here just so we have our correct amplitude at 2 and -2. And since we have a -2 to start, if I considered what is -2 cosine of 0, where my starting point would be, well, if x is equal to 0, cosine of 0 we know is equal to 1. And so this graph would actually start at -2 instead of +2, since we have that negative A value in the front. So for this specific graph, we would start the graph down at -2 instead. And then we'd have a cosine shape. So that would bring us to 0 up to our amplitude at our maximum, and then we'll go back down and end at our minimum at 2 pi again. So this will be kind of the flip, or the reverse image of our graph from before, except we have a different amplitude. So this would increase and then decrease back down. Like that. So if we compare these two, I'll try to bring them out. Notice that these will be kind of flipped over the x-axis. They'll be a mirror image of each other than just the height of our amplitude there when we have a negative amplitude. Any questions I can answer with that one before we maybe take a look at a live problem?
I think I have a question.
Yeah, go ahead.
How does the value of b impact the graph?
Yeah, so we'll add that b value in our next graph right here. So the b value is going to compress or widen the graph horizontally.
Okay, thank you.
Yeah, so we'll get to that in the next example. Yeah. Okay, so let's take a look at a live problem. If you want to live 4, we'll take a look at a graphic problem in there so you get a chance to take a look at those. The live assignment 4, you can join in. Let's see. Oh, each of these. This one. And yeah, we'll wait for this one and come back to it after I introduce the next step. Okay. So we'll for one more problem. So let's take a look at this next example, and then we'll take a look at a live problem. So in this case, we're just going to do a period shift for our sine function. So notice that in this case, we have an a value just equal to 1, so our amplitude doesn't change. But our b value here is equal to 4. The b value in that equation would be 4. So again, the period p is equal to 2 pi divided by the absolute value of b. So therefore, my period would be 2 pi over 4, or pi halves. So this is telling me a couple things. This is telling me that I'm going to go 4 cycles of sine in 2 pi. So that's what that b would be representing. 4 cycles in 2 pi. And it would tell me that 1 cycle is done over pi halves units. That would be an equivalent statement. So pi halves would be a full cycle of sine. So if I think about pi halves full cycle of sine, zoom in here to the interval from 0 to pi over 2. So I want to do a full cycle of sine in this interval. So we know from our previous problem that the sine function starts at the midline. And so we always want to start our sine function at the midline. This would happen to be at 0 for this function because we don't have an amplitude or a shift in our function. And since a positive sine function, we'll just increase to our amplitude and then come on back. So this sine function over 0 to pi over 2 we would just start at 0. 1/4 the way through, we'd be up at our amplitude. Halfway through, be back down to 0. 3/4 the way, we would go to -1. And then we'd be at pi over 2 to complete the cycle. So if we're measuring these out, this would be like pi over 8, 2 pi over 8, 3 pi over 8, and 4 pi over 8. We wanted to keep track of those fractions on this graph. And our graph looks like this. So that would be our first full cycle of sine in the 0 to pi over 4 range. Any questions with what that looks like there?
So instead of stretching out through 2 pi, it's just squished, i.e. compressed, because it's a over 4 is greater than 1, i.e.
Yeah.
compression.
Exactly,
Okay.
yeah. So this would be compressed, exactly, because the b value is greater than 1. So we call that probably just a horizontal compression.
Real quick, how were you able to get pi over 8 again?
Yeah, I just divided, if you think about pi over 2, that's our full length, and divide that by 4, you'll get pi over 8 for each of those sections. Because the sine function is kind of split into kind of 4 segments there.
I got you, thank you.
So certainly you can draw, if we were to draw this, and I think I have this in the solutions, but I won't take too much time to do it here. We could redraw, another sine function on this 3 more times to take back out to 2 pi to show that there's 4 of these within the length of 2 pi. But this would be our first rotation or cycle of the sine function there.
So each section would have something like that. Just repeat.
Yep, it would be just copies of this one after another.
How do we find the pi over 8, 2 pi over 8?
How did I find those?
Yes.
So yeah, just like the question before, I took that pi over 2 and just divided it by 4, because there's kind of 4 sections in a sine function. There's this section, and those 2 sections. So each of those are equal length, so just divide that full pi over 2 by 4, and you get pi over 8.
And the recurring sections, would they still be pi over 8? It just a repeat of the same thing? So
Yeah. So just draw one repeating section. So it would just go like this for the repeating section. And so this would be kind of the next cycle, just like that. And this would be 5 pi over 8. This would be 6 pi over 8, 7 pi over 8, and then 8 pi over 8, which is really just pi. So it would just be a repeating cycle just like this.
Okay, thank you. I just wanted to confirm my suspicions before,
Yep.
and not
Yep,
just
that's
rely on
exactly
what
right.
little I knew.
Yep. So the pattern just continues.
So you divide 2 pi by b.
Yeah. If you wanted, well, the b value just happened to be 4, so it would just be dividing by 4 every time. It doesn't actually matter what the b value is. So I just took my period length and divided it by 4 to find the length of each of those segments. Because there's always going to be 4 segments in a sine function.
Okay.
All right. Let's put these two things together with our amplitude and period. I want to make sure that we should be okay. So let's go through these, and I'd like to finish a couple more graphs here. We're going to keep with our cosine function, and this time we're going to have 2 different alterations to our graph. So notice here we have 3 cosine pi x over 2. So this would tell us that the amplitude is equal to 3. And we'll notice that the b value here, well, x over 2 would tell us the b value is 1/2. So in this case, we're going to actually expand because our b value is less than 1. So let's consider how that expansion is going to work. The first thing I could take into account is the a value being 3. So I'm going to just be kind of lazy on our graph here, but the amplitude here would be 3. And we'd have a negative 3 on the bottom when we would go to graph this. If my b value is 1/2, then I would consider my period against 2 pi divided by absolute value of b. And so that would tell us that this is 2 pi divided by 1/2. So if I do 2 pi divided by 1/2, I'll actually get 4 pi. So again, the period is telling me how long the length of one cycle. And so we're going to go through 1/2 of a cycle or of cosine in pockets. So this is going to be expanding. So we only have up to 2 pi. So we're going to do half of a cosine wave in this domain. All right. So if I'm going to do just a half of a cosine wave in this interval, remember that just looking back at our previous problem for a moment, our cosine function. Okay, there we go. Cosine function starts at our amplitude and then brings it down. So really we're only doing kind of this half of the cosine function. And we're just going to be expanding that over the 0 to 2 pi range there. So we're just doing that portion or half of a cosine function. So in this case, our graph would start at our amplitude, which would happen to be 3. And then we're only going to do half of the function. So at pi units, we'd have to be down at 0. And at 2 pi, we'd be just halfway through our cycle. And just to confirm these, we did y is equal to cosine of pi over 2. That would be when x is equal to pi. Notice that cosine of pi over 2 is 0. And so this would be 3 times 0, or 0. That's where we get our second point. And when x is equal to 2 pi on our function, we have 3 cosine 2 pi over 2, which is cosine of pi. And cosine of pi, if we looked at that on our graph, we'd say that cosine is -1 at pi units. So this would end up being -3, and that's where we get that second point. So that would be kind of an ugly graph there. Let's get a little bit more curvature there. So this would be really half of a cosine wave that we would have here. So this would be an expansion. All right. Any questions with the combination of these two?
Fractions stretch, solids squish, basically.
Right. Yep. Yep. The fractions will expand. The whole numbers larger than 1 will compress. All right, let's go take a look at one more graph to round this out, and then we'll have a couple applications to finish our class. So the last one we have is -1/3 sine 2x. So we'll start with our a and our b. If I consider my amplitude, so absolute value of a here happens to be 1/3. And then the b value, we'll notice, is this 2. So right after that, we can consider our period. So if I have a b value of 2, what would be my period?
Pi?
Yep, pi units. Excellent. Yep, so it'd be 2 pi over 2, or just pi units. So that means I'm going to do 2 full cycles in 2 pi units, or 1 cycle is going to take pi units. All right, so that looks good. And we'll notice that our amplitude here is 1/3. So let's change our bounds on that amplitude. We'll have 1/3 and -1/3 on the bottom. Okay. With that, let's now consider period. So we're going to be starting at 0, and we want to end at pi for our first sine wave because of our period being equal to pi units. Now, what did we say? If the sine function is at 0, what is the sine of 0? Where we start our sine function, is it at the amplitude or our midline? Excellent. Yep. On your right. So we start at the midline, which in this case happens to be y equals 0. So we start at the midline, and then we're going to do a regular sine wave, but we'll notice that the function has a negative to start. So this will be important. Just like when we started with a cosine that was negative, we started in the negative direction. This will be the same thing for the sine. So if I wanted to write this sine function out, I start at 0, 0. And again, since I'm going to do a full cycle between 0 and pi, I want to make a marker here at pi over 4 and 3 pi over 4, as those points will kind of give me kind of 4 sections to my graph here. So in this kind of 4 sections to my graph, I know I'm going to go decreasing first because of my negative on my sine function. So that will be down here. By pi over 2, we'll come back to 0. And then we'll hit our maximum at 3 pi over 4. And then back down to 0 in my first cycle endpoint. Now, just to confirm kind of that point for us, let's just say when x is equal to pi over 4 here, let's just confirm that in the equation. And again, the pattern kind of takes over from there, but we do want to confirm maybe that first point. If we have y is equal to negative 1/3 sine of 2 times pi over 2, or pi over 4, pi over 4. If I wanted to calculate this real quick, we could say this is negative 1/3 sine of pi over 2. And if we think about our unit circle, pi over 2 in the sine function is going to be 1. That would be at the top of our unit circle. So this would end up being just negative 1/3 times 1, which is negative 1/3. So that's where we get that first point. And then we follow the kind of the sine pattern from there. It would look like this guy right here. And we just simply copy this function a second time, and we'll just do it in a different color to view this. We copy these same points in that same order for the second round that function. So we go through 2 full sine waves in the matter of 2 pi units.
Professor, what would cause a sine function to have a midline other than 0?
Yeah, that's a good question. In kind of the videos that you'll see probably tomorrow, you'll see something like a function that looks like this, maybe like 2 sine of 3x plus 2. If you look at this plus 2, that's going to be changing the midline from 0 up to 2. So that would be a vertical shift there. So if you add something to the end of a sine function or a cosine function, that's affecting the midline.
Got it. Thank you.
Yep. All right, we got a couple more applications we can try to finish up before class end here. And these applications seem complex, but just by kind of looking at our graph, I don't think they're going to be too bad for us. So let's take a look at number 1. A weight is hung from a spring and set in motion so that it moves up and down continuously. The velocity of the weight at any time is given by the equation v is equal to 3.5 cosine 2 pi t, where v is measured in meters and t is measured in seconds. Find the maximum velocity of the weight and the amount of time it takes for the weight to move from its lowest position to its highest position. Okay, so one thing that might be helpful here is just to do a little sketch of this function. So let's consider that. If I look at my equation here, notice that the v equation will have an look at this function has an amplitude here a of 3.5 and it has a b value of 2 pi. So notice if we consider turning that into a period calculation, period again is 2 pi divided by the absolute value b. In this case, that there happen to be the same. So this would be 2 pi over 2 pi, or just 1. So this means that the period of this weight is going to be 1 second. That's what my input is measured in. So that period is 1 second. And so now we can consider maybe just making a sketch of this function. I know the amplitude is 3.5. And we also know the period is 1. So if we considered kind of making a graph into 4 sections, again, for a cosine function, we're going to do 1 full cycle of cosine in 1 second. So dividing that graph into 4 sections there, we can consider how to sketch a cosine function. The cosine always starts at our amplitude. And so cosine function starts at that high amplitude, and we'll draw our cosine in like so. This gives us an opportunity now to answer these questions once we have a little sketch given. So the first question that we want to consider is, what is the maximum velocity? So with our graph, what would be our maximum velocity here? Again, this is measuring velocity. Yep, exactly. Yep, maximum velocity. Will just be that 3.5. And in our units here, measured in meters per second. You can say 3.5 meters per second. And how much time does it take for the weight to move from its lowest to its highest position? So from the lowest to its highest position. Well, this is its lowest position. And its highest position, or its highest speed, would have to be just 1/2 of a second. For that second part, 1/2 second or 0.5 seconds. Excellent. Is there any questions with that application there? We have a similar application in number 2. Again, these are just playing off of the amplitude and the period, really. Oops. We want to do. Last example here, we'll take a look. So the current in an alternating circuit varies in intensity with time. If I represents the intensity of the circuit and T represents time, then the relationship between I and T is given by I is equal to 20 sine of 120 pi T, where I is measured in amps and T is measured in seconds. Find the maximum value of I and the time it takes for I to go through one complete cycle. So if I'm looking at these questions, I want to find the maximum value. Really just the amplitude. And we want the time it takes to go through one complete cycle. Well, one complete cycle we just call the period. So we're really asking a question, what is the period? And really, what is the amplitude? If we can find those two things in our function, I think we've got those two questions answered. So if I consider first the question of the amplitude, what is the amplitude for this circuit? Right? And how would we measure 20? What's the units of measure here? It would be our, amperes. Yep. So amplitude here would just be amperes. So the intensity I is just measured in amperes. All right. And how about the next one, the period? If I wanted to find the period for this function, we'll notice that the value for that sine function is 120 pi. We can convert that to my period. Take a moment to do that. What would be our period here? Okay, you guys are coming up with 1 over 60. That looks good. So we're really doing 2 pi divided by our b value, 120 pi. For those pi will cancel, I'll just have 60 over 1. So 1 over 60, and in this case, our cycle, or at least our period here is measured in, again, time units. So that would be seconds. Takes 1 over 60 seconds, or 1/60th of a second to go through a full cycle. So it's going pretty fast. All right. Any questions with that last example with the current in identifying those questions? All right, so that will wrap up section 4.1 and 4.2